Okay, so we're just going to briefly go through these, and then we're going to be looking at some of these in a little bit more detail, especially the Rutherford one.
Yeah.
So John Dalton, he said, as I said, he drew upon the ancient Greek idea of atoms. The word atomos means indivisible. It's a Greek word, and the Greeks, the ancient Greeks, said that they had this theory that matter, in other words, that's the scientific word for stuff, is made out of indivisible particles, which John Dalton decided to call atoms. But what he did say that it was that different elements, so that we had an idea of what an element was at that point, and he believed that
Mm.
different elements are made out of identical atoms. So, for example, gold would be made out of identical atoms, which we could call gold
Yeah.
atoms. So that bit he's got right. Then we go along to J.J. Thomson.
And with John Dalton, he thought about all but I'm pretty sure
No,
I think it was called positive.
I
Or
don't. I don't think so because I think that diagram seems to suggest that it's neutral. So
oh, so it has
how
no charge. He just thought there's no
Yeah,
charge.
yeah. He just thought there was no charge. However, then Thomson discovered electrons. Now, so he thought, well, these, and he called them corpuscles. Corpus, I don't know how you say that word, but I don't think you need to know that word. And he decided, well, maybe they're just kind of like embedded in this atom. Okay, and so, but because the whole thing had to be neutral and the electrons are negatively charged, then the rest of the stuff that the electrons were embedded in must therefore be positively charged and have an equal and opposite charge in order to cancel out and make the whole thing neutral. So,
Yeah.
so he's definitely onto something there. Now, the Rutherford scattering, which we'll talk about in a bit more detail in the next video, which is related to obviously what Rutherford came up with, it's basically challenging this model here, which he called the plum pudding model,
Yeah.
because it was like a plum pudding. We don't eat plum puddings anymore, but maybe we can think about it as a raisin bun or something like this, or chocolate chip cookie. But they had this stuff, the electrons embedded in with it, which is like the plums. Now, um, importantly, this the they had a rough idea of what the size of the atom was, and they had a rough idea of what the mass of the atom was. So they therefore can calculate the sort of average density of the
Uh,
of the of the atom, and they when so that's important. So they had a rough density, and um, it would be comparably low density. Okay, now as we know now through our current understanding of the atomic model, is that mostly it's empty space. Okay, the remaining the other three models would all support that idea that it's mostly empty space, and in fact, pretty much all of the mass is contained in the center, in the nucleus. Now, Rutherford conducted this experiment, which we will look at in a little bit more detail, where we fired um, alpha particles. I'm not sure if they really knew what alpha particles were, but they did know the
yeah.
size and the mass of the alpha particles, and therefore the density of these alpha particles, compared with the density of the atom. Alpha particles are extremely dense because, of course, alpha particles, as we now know, are just the nucleus of a helium atom. They're just two protons and two neutrons without the empty space around them. So very, 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 very dense. And the kind of analogy that they said was it's a little bit like firing cannonballs at tissue paper. So the thought of a cannonball bouncing off was clearly never going to happen if the plum
Yeah.
pudding model was true. The density of the alpha particles so much higher than the density of an atom. But if it turns out that the density is not equally spread, like Thomson believed, then there are going to be parts of the atom which are high density, which we presumed would be in the center. And
Yes.
and that part would therefore be so high density, it really did, in fact, bounce the Av particles back. So that was quite a discovery. We also had some like smaller deflections, and that would suggest that not only is the mass high in the middle, but it's also positively charged. As it came closer to it, it was repelled, because we knew that Alf particles are positively charged. So now, what we need to know is what Rutherford hadn't discovered at this point, and that is how the electrons are orbiting it. He just presumed that they were orbiting it, they were going around the outside, the nucleus was in the middle. He didn't know about how they're orbiting it. He didn't know anything about these shells, which Bohr came up with. He also didn't know anything about the neutron. He didn't know anything about the neutron at all, but he agreed with many of the correct things from the previous models. So, in fact, he brought the electrons in from Thomson's model. He agreed that different atoms from different elements would be different in some way, but that's about it. So Niels Bohr, well, what did he believe? What did he come up with? So he stated that electrons are moving around the nucleus in fixed sizes and energies. So we can call these energy levels, or you can call them shells. And maybe at an earlier level in education, you might think of them as orbits. There's an issue with using the word orbits, but I won't get onto that just yet. Shells seems a strange word to use. We don't say that the Earth orbiting the Sun is in a shell, right? So it doesn't seem to make any sense, but there's an explanation for that, which we will get onto when we look at Erwin Schrödinger. So he said that electrons don't move in set paths around the nucleus, but in waves. They essentially are everywhere at once, strangely enough. They don't. So electrons, as it turns out, all matter, but electrons are very small, and this can be observed more easily, that they behave as particles and as waves. Now, this is covered a lot more closely at A-level physics, but essentially, this is why we use the word shell, because it's not here and now it's here and now it's here. It's everywhere at once, weirdly enough. And so that's why we use the word shell, and the energy level we use because it actually can't be somewhere between there and there. It can only be here or here or here. And so it kind of like snaps from one place to another, almost like teleporting from one place to another. And all those kind of weird, like the idea of it being everywhere all at once and sort of teleporting from one place to another, that's all under the topic of quantum physics. So it's a little bit blurry, so you can't quite make out some of this. Well, we might be able to make it out if we concentrate, but those are the key points behind the different models. You'll mostly want to know about this one here, why this disproved that. So that's what we'll have a look at in the next video. Okay.
Yes.